So after water, we now derive the transport equation for vapor. Again, we will follow the clearly defined mechanisms for this transport. So for vapor, the transport mechanisms are molecular diffusion and gas pressure driven flow. We're going to develop considering these two mechanisms. Recap that total flux in general can be written as diffusive plus convective. So there is a diffusive part and a convective part. As applied to vapor mass flux, the two processes are again diffusion and flow. However, the diffusion here in case of vapor, it's vapor in air. So it's a binary system, and in this diffusion, the binary diffusion, the formula has to be slightly rewritten from this very simple version that we did for just simple two component. Here the binary diffusion is written still Fick's law, but in a slightly different form. And as we change from concentration with various mass units to here mole fraction and so on, we get all these other factors come in, which are molecular weights and so on. So the first part is due to diffusion of vapor in air, which is Fick's law rewritten for binary diffusion. The second part has to do with flow. So the flow is from high pressure to low pressure. This flow is written using Darcy's law, of course. Velocity comes from Darcy's law, and then velocity is like volumetric flux. So we multiply by the density of vapor to get the mass flux. So together, this formula now takes care of the vapor flux in a porous medium. As we did for liquid transport equation, the vapor transport equation is now derived by substituting the vapor flux that we just derived into the vapor conservation equation. So here is my vapor conservation equation, and in there I substitute the NBX, the vapor flux equation that we just derived on the previous slide. So we're going to substitute all of these into the vapor flux term. And now if I do that, the rest of it is just going to be algebra, just plugging in. And so we have del CB del T, that term here, and then del X of this entire quantity is equal to I dot. Remember, I dot is a source term for the vapor equation because liquid is being converted into vapor, so it's positive term. And now if I rewrite this, we can also write it as del X of rho V times the rest of it is really velocity of gas, and then on this side this is the diffusion term, and then the evaporation term. Finally, we generalize this into 3D and in arbitrary coordinates by writing it this way. Again, I want you to see that this is the storage term that has SV in it for the vapor saturation. So we're really solving this equation for this vapor saturation. This is the convective term, and that has the gas velocity. So the velocity that we have is the gas, is for gas, meaning vapor and air together. And then this is my diffusion term, diffusion term, and that diffusion is vapor in air, and this is water to vapor, that way. Okay, so then this is the equation that we use to solve for the vapor saturation, SV. So back to our map, and we'll try to summarize the vapor transport using the map. And in this case, we're going to only write the vapor transport part of it. So vapor transports due to either bulk flow or diffusion, and bulk flow of vapor is due to gas pressure. The driving force is gas pressure, and diffusion of vapor is that of it's that from molecular diffusion. And then finally we also have a source term, which is positive because vapor is being generated.